This will be the last lesson in our series on chemical equilibrium. We know that when the rate of the forward and reverse reactions are equal, we have a state of chemical equilibrium. We know how to write KEQ expressions. We know how to solve them and interpret them. We also know how to calculate the concentration of a reactant or a product when given all the other concentrations and the KEQ. And hopefully you feel very comfortable with those concepts, which will be assessed on your quiz. The last piece of the chapter in the quiz is going to focus on Le Chatelier's principle. Before we get there, I just want to reiterate that when you write equilibrium constant expressions, you include gases and aqueous substances only. No solids, no liquids. Their concentrations and densities are constant, so we don't include solids or liquids in KEQ expressions. I didn't do it to you on the quiz, but it is in the lab and you'll see it on your test. So remember, no solids, no liquids in equilibrium constant expressions. I'm not going to cover solubility product constants at this time. For those of you who are interested, I'm more than happy to show you tomorrow. Tomorrow will really just be a practice day. Unless you would rather do the lab tomorrow, we can discuss it at the end. So we're going to talk today about Le Chatelier's principle. Now, when you read about this in textbooks and try to understand it, sometimes it's very, very tricky. So I'm really going to break it down to the bare bones, show you a couple of little tricks, and then that way you'll be much more successful with this concept. There are factors that can alter equilibrium. When you've reached a state of chemical equilibrium, the rate of the forward and reverse reactions are the same. They're equal. Well, you can do something to disturb a system at equilibrium. You can alter the concentration of a reactant or product. You can alter the temperature of the system, or you can alter the pressure or volume of the system, and that will affect equilibrium. When you perturb the system in some way, the system will respond by at least partially undoing what you have done. This is known as Le Chatelier's principle. We'll be talking about it today, and then we'll explore it in the lab in more detail from a colorimetric type standpoint, where you'll see changes in color to determine which way equilibrium shifts. And we'll come back to that a little bit at the end from the video we watched the other day. So the factors that we're going to be looking at today, also known as stresses, which affect equilibrium, not to be confused with kinetics. Be careful here. That's where it gets tricky, the two chapters together. So we're going to look at some factors or stresses that affect equilibrium. And the factors that we're going to be looking at today include concentration, temperature, and pressure or volume. We're first going to focus on concentration and temperature. And I'm going to make a blanket statement here that we will implement as we go through alterations in concentration or pressure. What you're going to see is that if you increase the concentration of a substance or the temperature of the system, what you will see is that chemical equilibrium will shift away from that entity. In contrast, if you decrease the concentration of a substance or the temperature of the system, chemical equilibrium will shift toward that entity. And I will explain what that means in great detail in just a minute. Increase away, both starting with the value, decrease toward. And I'll show you what I mean. I've set up a grid for you to fill in to explain this concept much simpler than just memorizing things written in a textbook or in your notes. So we're going to try and keep it simple in that regard. So in your notes, you have the following table. We have a reversible reaction. A and B are reactants, C and D are products. Energy as shown is on the left side of the equation. Is that reaction endo or exothermic? Endo, and the delta H would be positive or negative? Positive. And this is where you've learned things in a previous chapter that can come in handy. What we're initially going to do is look at the stress of concentration. If I increase the concentration of A, I'm adding more of substance A to this system that's at equilibrium. If I increase the concentration of a substance, I will shift away from that substance in order to at least partially use what I have added. So when I increase the concentration of A, equilibrium will shift in the forward direction to utilize added A. So when you increase, you shift away from that substance. You're shifting, equilibrium is shifting in the forward direction. Now, if the reaction is working better in the forward direction, I initially increased A. That was the first thing I did. But with the forward shift in equilibrium, what's going to happen to A and B as the reaction goes forward? Their amounts will decrease because they'll get utilized. Now, it doesn't decrease as much as you added because it only partially undoes what you've done to it. With the forward shift in equilibrium, what happens to the concentration of products? They will increase because they get generated. If the forward reaction is favored, the reactants will decrease, the products will get generated in whichever direction the arrow points to tells you what gets made. Yes.
So if you decrease like the value of A, then it's gonna shift towards that end?
It'll shift toward it. We're going to do that next in a decrease. So Chris, help me out here. In the second example, and I think this is where you were going with your question, we're going to decrease B. Your best approach working these types of problems is to put that decrease right over the substance. When you decrease, do you shift away from it or toward it? Toward it. You shift toward it so you can replace some of what you've lost. So with the decrease in the concentration of B, equilibrium will shift in the reverse direction to replace removed B. I'm writing in pencil. Can you see that?
Yeah.
Okay. I can write in ink. I just have to scribble on it in pencil. Now, when we shift to the left or reverse direction, we initially decreased B. But when we shift to the left, what happens to the amount of A and B? They will increase because they're getting made, and C and D now will get consumed, so they will decrease. Whenever you shift forward, reactants will decrease, products will increase. Whenever you shift in the reverse direction, the reactants will increase, the products will decrease. Now, if we increase C, a product, and Chris, does that answer your question? Yeah. I thought so. Okay, good. If we increase C, in which direction will equilibrium shift? To the left, to utilize or use added C. So we initially increase C, but with the reverse shift in equilibrium, what will happen to C and D? They're both going to go down, and the reactants will get generated. Concentration. When you increase the concentration of a substance, equilibrium will shift in the opposite direction of that substance in an effort to at least use some of what you added. When you decrease the concentration of a substance, equilibrium will shift toward that substance in an effort to at least partially replenish what you removed. Temperature works very similarly, but you've got to know whether the reaction's endo or exothermic. We established that this reaction is what? Endo, because energy is on the reactant side or left side of the equation. Feed the temperature into the energy term. When we increase energy, when we increase temperature, we're going to show the up arrow over the energy. When we increase temperature, equilibrium will shift in the forward direction away from the energy term to use added heat. With a forward shift in equilibrium, what happens to reactant concentrations? They're going to decrease, they get consumed, and products will increase. Yes?
So for the outcomes, you really just have to worry about if it's forward or reverse, right?
If you know it's forward, you know it's going to increase because it'll be product, and if you know it's reverse, then you know the reactants will increase. The only place it gets a little tricky is with the increase and decrease, because it's whatever you do initially and then whatever happens undoes that, or at least partially undoes it. So if you decrease temperature, equilibrium will shift to the left to replace heat lost or lost heat, whatever you want. When you shift in the reverse direction, then A and B get generated, C and D get consumed. Does that make sense? Good.
So for temperature, it just depends on which side the energy's on.
Correct. This is an endothermic reaction. Now, when you look at what's written in textbooks or online, I'll show it to you, but I think you're going to have a much easier time going this way. So concentration and temperature are two stresses or factors that affect chemical equilibrium. In terms of what's in your notes, a lot of this is written out in excruciating detail. A couple points I want to make. We know one factor that affects equilibrium is concentration. When you increase reactant concentration, equilibrium will shift in the forward direction to utilize that particular reactant. We know with the forward shift, reactant concentrations will decrease and product concentrations will increase. Keep in mind one of the reactants will go up and then down. Please note that the value of KEQ is not changed when you alter concentration. The only factor that alters the value of KEQ is temperature. Only temperature alters the value of KEQ. And all of this that is written here we mentioned already. Let's take a look at this first example and make sure that we can not only predict which way equilibrium will shift, but also explain why equilibrium shifts in that direction and what happens to reactant and or product concentration. So in this first one, we want to know whether the forward or reverse reaction is favored. We want to indicate whether the concentration of reactants or products increases, and we want to explain. So in this first equation, we've got a reversible reaction showing synthesis of ammonia from nitrogen gas and hydrogen gas. If I were to increase the concentration of nitrogen gas equilibrium would shift in which direction? You are correct. Equilibrium would shift in the forward direction or to the right to use added nitrogen gas. When equilibrium shifts in the forward direction, what happens to, no, it says indicate whether the concentration of reactants or products increases. So what increases, reactants or products? Products. So you'd get an increase in product concentration because those ammonia would get generated. It depends where the explanation is coming in, so let's write it in. So we're going to shift in the forward direction to use added nitrogen gas. We're going to increase product concentration because with forward shift or with forward equilibrium shift, NH3 gets generated. If we were to decrease the concentration of hydrogen gas, equilibrium shifts to the, if we decrease, we have to shift toward it, and it's on the left, so equilibrium shifts to the left to replace removed hydrogen gas. And as a result, what will increase, reactants or products? Will increase the concentration of reactants because with reverse shift, reactants get I'm going to write made because it's shorter. Pen's going to fall off the book. All right. If we decrease the concentration of ammonia, equilibrium shifts to the correct? To replace removed NH3, and what will increase? Yeah, that one's a little tricky because it actually decreases more than it increases, but it's the only thing that's going to increase. So we're going to increase product concentration because with forward shift, forward equilibrium shift, I probably should say equilibrium there too. Ammonia gets generated. It's not so bad. It's kind of fun. We've also already mentioned the stress of temperature, and we'll be looking at the stress of temperature in the lab. We already looked at it, but you didn't really know what you were looking at when we watched the video, but we'll go back and take a look. See? It'll go back up, don't worry. With temperature, when you increase temperature, you've got to shift away from the energy term. It says equilibrium will shift in a manner that favors heat absorption. When you decrease temperature, equilibrium shifts in a manner that favors heat release. And we're going to look at these examples here. I'll explain those statements in a little more detail. We're still going to play with the concentrations here to make sure you've got that concept down. This actually is the reaction we looked at initially where you had brown nitrogen dioxide and colorless dinitrogen tetroxide. And this is an exothermic reaction. Delta H would be negative. If we increase the concentration of dinitrogen tetroxide, in which direction will equilibrium shift? It'll shift to the left to use added dinitrogen tetroxide. The concentration of what will increase? Concentration of the reactant will increase because with reverse equilibrium shift, NO2 gets generated. If we decrease the concentration of nitrogen dioxide, again, always easier to work by putting that decrease in, equilibrium shifts to the correct, to replace removed nitrogen dioxide. And when you shift to the left, we're going to get an increase in reactant concentration for the same reason we stated here. And here's our temperature piece. Now temperature is the only factor that alters the value of KEQ. We'll get back to that. When you decrease temperature, and this is why it's very helpful to have the energy term in the equation, equilibrium will shift to the right to replace heat lost. And when we shift to the right, the concentration of product increases because with forward equilibrium shift, N2O4 gets generated. So we've got stresses of concentration and temperature affecting equilibrium. And we approach them very, very similarly in terms of our analysis of the equilibrium shift as well as whether the reactant or products increase. The other stressor factor that we want to talk about is pressure. We talked about pressure when we talked about gases. Pressure is equal to force per unit area. What do you know about the relationship between the pressure and volume of a gas? They are inverse. So with bubble wrap, if you push down on that bubble wrap, the volume's decreasing, the pressure's increasing, finally the pressure becomes so great that the bubble pops. When you increase the pressure of a system, equilibrium will shift in the direction of the smaller volume of gaseous particles. You determine the volume of the gases based on your stoichiometric coefficients. So what you're going to see here as you increase pressure of a system, equilibrium shifts in the direction that has the smaller volume of gases. If you look at this example here, you would have a coefficient of 2, so 2 mils or 2 liters of gaseous reactant. On this side, you have a coefficient of 1. You have 1 mil of gaseous product. In this example, if you increase pressure, equilibrium would shift in the forward direction because the volume of gaseous product, which is 1 mil, is less than the volume of gaseous reactant, which is 2 mils. If you decrease pressure, you'll shift in the direction of the larger volume of gas, so you would shift in the reverse direction due to that inverse relationship of pressure and volume. This is written in your notes. I'll give you several examples. It says if the pressure of a system is increasing, now you're not just increasing the pressure on one side of the equation, you're increasing the pressure of the system. Boys, let's focus. If you increase the pressure of the system, equilibrium shifts in the direction that favors the smaller volume of gaseous particles. You determine that from the stoichiometric coefficients of gases only. We know that pressure and volume are inversely related according to Boyle's law. If you decrease pressure, equilibrium is going to shift in the direction that has the larger volume of gas for the same reason we talked about. If, however, the volume of gaseous particles in the reactants and products is the same, altering pressure has no effect on equilibrium. You can see that here. In this example here, you've got 1 plus 1 is 2 volumes of gas, let's say 2 mils of gaseous reactant. end, you've got 2 mils of gaseous product. If the volume of gaseous reactant and product is equal, increasing or decreasing the pressure has no effect on chemical equilibrium. If, however, you look at this example here, this one's a little bit tricky. What is the volume of gaseous reactant? You have 2 mils of gaseous reactant. And what is the volume of gaseous product? 0, because that's a solid. So if you increase pressure, equilibrium is going to shift in which direction? The one with the larger volume or smaller volume? Smaller volume. So equilibrium in this case is going to shift to the, I don't know why I can't write on there. I was trying. Yeah, oh well. I've got it right here. So if we increase pressure, equilibrium's going to shift in the forward direction because the volume of gaseous product, which is 0 mils, is less than the volume of gaseous reactant, which is 2 mils, and we know that pressure and volume are inversely related. All right? And we're going to do several of those, and that's the last piece of the puzzle, and then we're just going to practice.
For the sake of the quiz, can we just do like the greater than or less than?
Yeah.
Okay.
You can do it just like that. You don't even have to write gaseous. You can write G and G.
Okay.
But I think I do ask for a specification of quantity of volume.
Wait, what's it say?
What does what say?
It's decreased.
Huh?
0 mils.
0 mils. All right. So in the next example, we've got ammonia and oxygen gas generating nitrogen monoxide and water. And I don't think I really wanted to show you that energy term. I think I would have preferred to have said this, and you would know that this is exo or endothermic. Exo, because delta H is negative. So then you'd put the energy term on the right side of the equation. And that's shown, going to be shown here, because I split the paper by mistake. Oopsie. So we've got 4 moles of ammonia plus 5 moles of oxygen gas. We've got 4 moles of nitrogen monoxide gas and 6 moles of water vapor. And I'm going to put E for energy right there because it's an exothermic reaction with a negative delta H. Alrighty, let's go. If we decrease pressure, equilibrium will shift in the direction of the smaller or larger volume. Larger, because they're inversely related, right? So we've got to figure it out. 4 and 5 is 9 mils of gaseous reactant. 4 and 10, whoopsie. 4 and 6 is? Sorry. If we decrease pressure, equilibrium will shift to the right because the volume of gaseous product, which is 10 mils, is greater than the volume of gaseous reactant, which is 9 mils, and we know that pressure and volume are inversely related. Or you can write Boyle's law. Spelled correctly.
Can we just put boil?
No. Robert Boyle. All right, here we go. If the concentration, this is just putting it all together. If the concentration of nitrogen monoxide is decreased, equilibrium will shift. Equilibrium will shift to the right or forward direction to replace nitrogen monoxide removed. Now, when you shift in the forward direction, what happens to the concentration of reactants? They will decrease because they get consumed. If the temperature of the system is increased, if we increase the temperature of the system, equilibrium will shift to the left to use the heat added. Do you want to try number 3? You want to do it together?
Yes.
Okay. Is it making sense though? All right, Haley, you're up. Oh, yes. I'll help you. We've got the synthesis of ammonia from nitrogen gas and hydrogen gas. We've got delta H is equal to positive 56.2. The first thing I'm going to establish, you got it. So we're going to put energy here or here? Correct. Definitely want to address that. Alrighty. Now, if we decrease pressure, are we going to shift equilibrium to the side with the smaller or larger volume? Definitely larger because of the inverse relationship. So we've got, this is just number 3. We've got 1 plus 3 is 4 mils of gas, and we've got 2 mils of gas. So equilibrium will shift to the correct. And that's because the volume of gaseous reactant, which is 4 mils, is greater than the volume of gaseous product, which is 2 mils. And we know that pressure and volume are inversely related according to Boyle's law. Alrighty, who else needs some extra work? All right, Hannah, go ahead.
It will shift to the right?
I don't know, which one? If you decrease ammonia, you have to shift toward it, so it's to the right to replace ammonia removed. Alrighty, if we decrease the concentration of hydrogen gas, equilibrium will shift to the left to replace H2 removed. By shifting to the left, you'll synthesize the reactants. If the temperature of the system is decreased, go ahead, Caitlin. Oh, you're so ready. If the temperature of the system is decreased, it will shift to the left to,
Replace the heat loss.
you got it.
I didn't know.
That's all right. You were ready. Good job. This is Le Chatelier's principle. When you disturb or perturb a system at equilibrium, the system will respond in such a way to at least partially undo what you have done. Question.
If the concentration of a reaction is decreased,
Reactant.
reaction is going to go
That is correct. Questions on Le Chatelier's principle? On this?
Yeah. You remember on the question I showed you? Like, how do you know when to go by moles or volume? I'm still confused.
Your explanation should be volume, but moles will work too.
So if you do the other way, you're fine? Oh, okay.
But not in here. In regard to your classwork, I initially said you could do through number 8. You actually could have done through number 9. We are going to omit 10 through 12. Don't scribble it. Some of you may want to do it tomorrow. I already hear scribbling. But now you can do 13 to the end. Now, I would do 1 or 2 of them today because tomorrow we've got a period to practice, and we do need to negotiate some things that we'll discuss off film. Any questions in regard to chemical equilibrium? What will be addressed on your quiz is listed at the end of your notes. Oh, I did want to show you one thing. That video link is a good review of Le Chatelier's principle if you need another review. If for some reason you missed the lab, a lot of the lab is shown in that YouTube video. And the only other thing that I wanted to go back and mention was gone. I'll find it. Don't worry. We looked at the video the other day. And we initially had the brown gas of nitrogen dioxide being converted to the colorless gas dinitrogen tetroxide. And what we saw here is that in the hot water, it turned brown. And this is what your lab's going to go into. We had this reaction. This was one of the first things we looked at in this chapter. And so what we had here is when we increase the temperature, we saw the brown color. And when we decrease the temperature, we saw clear. Is this reaction endo or exothermic, and why? And this is what your lab will go into. Go ahead, Sam.
It's exothermic.
Why?
Because when you increased it, it went back towards the brown. So the energy has to be on the product side.
You are correct. When you increase temperature, you got a reverse shift in equilibrium, generating the brown color. When you decrease temperature, you got a forward shift in equilibrium in an effort to replace the heat lost and the clear color. And your lab will explore that, which will be very good for you. You have that video link if you want to go back and watch it. Also, at the end of the chapter, it does indicate exactly what will be on your quiz, and we will negotiate that date, as I know you have impending test dates on multiple days. Questions here? Once you go through the classwork in class tomorrow, I think you'll have a much higher level of understanding of this concept, but hopefully you have a feel for it at this point, yes? It's kind of fun.
It's just not hard.
It's not hard and it's fun. Any additional questions?